Hey there, and welcome. So, you've probably been there, staring at a triangle that doesn't have that nice, neat 90-degree angle, and suddenly all your usual math tricks don't quite work. Well, today, that all changes. We're going to add a seriously powerful new tool to your geometry toolkit, one that lets you solve pretty much any triangle you come across. Let's get right into it. So here's our game plan. First, we'll talk about where our old friend SOHCATOA kind of hits a wall. Then, I'm going to introduce you to the law of sines. After that, we'll roll up our sleeves and solve some triangles together, step by step. And of course, we'll cover the common mistakes so you can avoid them. Finally, we'll see how all this math is actually used out in the real world. Okay, first things first. To really get why the new tool is so great, we have to understand the problem we're trying to solve. So let's talk about why our trusty old trigonometry rules just don't always cut it. I mean, think about it, right? We've all gotten pretty good at using SOHCAHTOA to find missing sides and angles. But that entire system, the whole thing, it depends on one critical piece, a hypotenuse. And you only get a hypotenuse in a right triangle. So what do you do when you're looking at a triangle that just doesn't have one? And this really lays it out perfectly. Over on the left, that's our comfort zone, right? The right triangle. SOHCAHTOA is king there. But on the right, we've got what's called an oblique triangle, which is really just a fancy name for any triangle without a right angle. And up until now, that big question mark has been a real gap in what we can solve. Well, today we're going to erase that question mark for good. So let's get to the solution. It's time to meet this super elegant, incredibly useful formula that works for any triangle. It doesn't matter if it's a right triangle or not. And here it is. The law of sines. It looks simple, and honestly, the idea behind it is just beautiful. All it says is that for any triangle, the ratio of a side's length to the sine of its opposite angle is the same for all three sides. So side A always pairs with angle A, side B with angle B, and C with C. This one little relationship, it unlocks so much. Okay, so this is super important, knowing when to pull this tool out of your toolbox. The law of sines is your go-to whenever you know two angles and any side. That could be an angle-side angle setup, or ASA, where the side is squished between the two angles you know, or it could be angle-angle side, AAS, where the side isn't between them. Now that third case you see, SSA, that one's a little tricky. We call it the ambiguous case, and we'll tackle that in another lesson. Now here's a little whoa moment for you, something that shows just how cool this formula is. It turns out that that ratio we talked about, A over sine A, B over sine B, they're all equal to the exact same thing. And that thing is the diameter of the circle that you could draw perfectly around the triangle, hitting all three corners. It's this beautiful hidden piece of geometry. All right, enough with the theory. The best way to really understand a tool is to actually use it. So, let's walk through a few examples together and see the law of sines in action. Okay, let's start with an angle-angle side, or AAS, case. We've got two angles, 40 and 60 degrees, and we know side A is 10, which is opposite that 40-degree angle. We want to find side B. So step one, we just set up the proportion from the formula. 10 over sine of 40 degrees equals B over sine of 60 degrees. Step two is just a little algebra to get B by itself. And when you punch that into your calculator, you get your answer. Side B is about 13.47. See? Pretty straightforward. All right, next up, an angle-side angle problem. This time we know two angles, but the side we know is the one between them. Now, wait a second. We can't use the formula right away because we don't have a side and its opposite angle paired up. But that's an easy fix. Step one is always to find the third angle. We know they all add up to 180, right? So angle B has to be 60 degrees. And just like that, we've got our pair, side B and angle B. From there, it's business as usual. We use the law of sines to find the other two sides. Okay, let's put it all together and solve a whole triangle. Find every missing piece. It's another ASA triangle, so what's our very first move? You got it. Find that third angle. Angle B is 180 minus 35 minus 80, which gives us 65 degrees. Now we have our key pair, side B and angle B. And with that one pair, we can find everything else. We set up one proportion to solve for side A, then another one to solve for side C. A couple of quick calculations, and boom, the entire triangle is solved.
Okay, this formula is awesome. But like any powerful tool, there are a couple of super simple mistakes that are easy to make. Let's make sure you know what to watch out for so you can nail it every single time. So before I just tell you, take a guess. Just thinking about the formula and the steps we just did, where do you think people trip up the most? I'll give you a second.
And here they are. Number 1, mismatching the sides and the angles. It sounds simple, but you've got to be careful that you're pairing side A with angle A, B with B, and so on. Get that mixed up and the whole thing falls apart. Number 2, and this one is a classic, your calculator mode. If your problem is in degrees, your calculator absolutely must be in degree mode. If it's secretly in radian mode, your answers will be complete nonsense. So my advice, always check your mode before you start. So, it's cool that we can solve for x on a piece of paper, but does anyone actually use this? Let's zoom out a bit and see where the law of sines pops up when you're not in a math class.
And this is where it gets really cool. Imagine you're a surveyor and you need to figure out how wide a giant canyon is. You obviously can't just stretch a tape measure across it. But what you can do is stand on one side, measure a baseline distance between 2 points, and then measure the angles from those 2 points to a tree or a rock on the far side. You've just created a triangle. And with the law of sines, you can calculate the width of that canyon without ever having to leave your side.
So there you have it. You're not stuck in the world of right triangles anymore. You now have this incredible tool that works for any triangle, a technique that real surveyors and astronomers and engineers use to figure out the world around us. You basically have the power to measure the unmeasurable. The only question is, what are you going to measure first?